Hawkins. This is my Lab 5 video lab report. I'm going to be covering the magnetic braking with Faraday. Alright, just a quick little introduction. The purpose of this lab is to make observations and record data of a magnet falling through a conductive tube of aluminum foil. We want to model this experiment computationally and compare the measured data and results with the computational predictions. Just a quick little preview of our results. Our experimental fall time that we recorded in class was 1.304 seconds, and the computational fall time was a little bit shorter than that at 1.044 seconds. These are the physical concepts used. The biggest ones are obviously Faraday's law, as the title insinuates, and then also the Biot-Savart law and Lenz's law. And then, as with just about any lab experiment you're going to do in this class, Newton's second law plays a big role. The biggest assumptions you have to make when going into this lab report is that the bar magnet acts as a magnetic dipole, that you can neglect air resistance, and that the aluminum foil acts as a non-ferrous conductive tube. For the experiment itself, you want to treat the aluminum foil and the bar magnet as a system, and everything else as the surroundings. The most important initial condition is that you want to treat the bar magnet as magnetic dipole, as said in the assumptions. For our procedure, you want to assign the north pole of the magnet with the magnetometer app that you can get on your phone. You want to drop the magnet into the tube and record the time it takes for the magnet to exit the tube. To normalize your data, you want to repeat this 5 times. Here's what our data looks like. Pretty standard. You can see what went in and what came out to get our average drop time, which is recorded at the bottom. Just a quick little preview of our GlowScript model. On the left, like I said, you can see all of the calculated values from the experiment. And on the right, you can see the GlowScript within VPython, how I edited all the values to get the desired outcome, which is obviously probably pretty similar to what all of y'all did. Here's more coding for the GlowScript. It's just very standard, making the formulas to be what you want, plugging in your initial conditions, and then just having everything map out. Here's the map that I got from the GlowScript. I think it's pretty standard. It's about what I expected to see going into the foil. It's got it's increasing velocity, but then through the foil, it reaches that point with the mu value, and then it stays around there until it leaves the pipe. The main sources of error that we thought was timing could have been off starting the timer. Anytime when you're thinking about 0.2 seconds between our value and the real value, I mean, that's around the average human reaction time, so it makes sense that we could have just not started the stopwatch immediately as the bar was dropped. And also releasing the magnet, we might not release it perfectly with the north side facing up. It could be at an angle, and this would have also affect your results. Understanding just like the simulation that I showed before, the intensity of the coloring of the tube indicates the magnitude of the current flowing through the ring. Red and blue indicates the current flowing in opposite directions, which color corresponds to clockwise. If you're looking at it from above, like I did, red was counterclockwise, and if you're looking at it from below, the blue was clockwise. So if you were to flip the system around, the directions of the net magnetic field would obviously be opposite. If we had conducted more trials of the actual experiment, we could expect that our trials would kind of start to reach a more accurate number closer to the computational value. And then what does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? At the start, before you enter the tube, obviously there's a large force due to the force of gravity. And then while it's in the aluminum foil, the gravity and the magnetic forces are equal, which is why it stays at a constant velocity. And then obviously at the end, the gravity starts acting on it more heavily again. Just for the discussion questions, the big one is obviously, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would increase, the magnetic force would also increase, and therefore the fall time of the magnet would take longer. And then secondly, what if the hole or slots were cut into the tube? How would this affect the ring currents in your model? The induced current would decrease, the magnetic force would decrease, and therefore the fall time of the magnet would take less time.